Good morning. Today we'll start with differential analysis of fluid flow. In chapter we derive the differential equation of fluid motion, namely conservation of mass, quantity equation, and Newton's second law, Navier-Stokes equation. This equation applies to every point in the flow field and thus enable us to solve all the details of flow everywhere in the domain. Also, this equation must be combined when necessary with additional equations such as equation of state and equation of energy. We provide step-by-step procedure for solving this set of differential equations of fluid motion and obtain analytical solutions for several simple examples. So introduction, let's take an example of this dish. So the fluid is flowing. So we have to select a control volume. This is flow into the control volume. This is flow out. So in case of a wind flowing around a satellite dish, a rectangular control volume is taken around the vicinity of the satellite dish as sketched. If we know the air velocity along the entire control surface, we can calculate the net reaction force on the satellite dish. That is, this is your reaction force here. So the interior of the control volume is in fact treated like a black box in the control volume analysis. We cannot obtain detailed knowledge about the flow properties such as velocity or pressure at points inside the control volume. Differential analysis, on the other hand, involve application of differential equations of fluid motion to and every point in the flow field over a region called flow domain. So this is your flow domain. You can think of differential technique as the analysis of millions of tiny control volumes sketched end to end on the top of each one another all throughout the flow field. In the limit, as the number of tiny control volume goes to infinity, the size of each control volume shrinks to point. The conservation equation simplify to a set of partial differential equations that are valid at any point in the flow. When solved, these differential equations yield details about the velocity, density and pressure at every point throughout the entire flow domain. In fluid flow problems in which air density and temperature changes are insignificant, it is sufficient to solve two differential equations of motion: conservation of mass and Newton's second law, conservation of mass of linear momentum. For three-dimensional incompressible flow, there are four unknowns, that is velocity, u, v and w component, and pressure, and four equations: one from conservation of mass, which is a scalar equation, and three from Newton's second law, which is a vector equation. So these set of four equations are solved simultaneously for four unknowns. In addition, boundary conditions for variable must be specified at all boundaries for the flow domain. We have now computer are used to solve these equations. Conservation of mass and the quantity equation. You can see here, this is our control volume. This is conservation of mass for this control volume. That integral of change in density with respect to time into dV for this control volume plus integral over the control surface with density into volume dot n dV must be equal to 0. So this is your node transport theorem for this control volume, where n is the vector which is normal to the surface, v is the velocity, d is this area of this surface. So this equation is valid for both mixed mass and moving control volumes, provided the velocity vector is absolute velocity. When there are well defined inlets and outlet, we can rewritten as, we can also write in this form: del p by del t into dv control volume is equal to mass in minus mass out. In other words, the net rate of change of mass within control volume is equal to the rate at which the mass flow into the control volume minus the rate at which the mass flow out of the control volume. So it applies to any control volume regardless of size. We can replace this control surface integral with the help of Gauss divergence theorem. So the divergence theorem allows us to transform a volume integral of a divergence of a vector into an area integral over the surface that defines the volume. For any vector g, the divergence of g is defined as del dot g into dv over control volume is equal to closed integral over the surface g dot n into dA, means volume integral can be converted into surface integral. The circle on the area integral is used to emphasize that the integral must be evaluated around the entire closed area A that surrounds the volume V. Now in this equation, this is g is a vector. This replace this g with density into volume vector, and when you substitute in this equation and replace this equation here over the control surface with the control volume, you will get this equation: del dot density V, this is your again, this G vector is replaced by this vector into dV over control volume. Now we have both equation in control volume. You can combine these two into one. This is control volume integral into this equation. Now integration of a term cannot be 0. It can be 0 only when this term is equal to 0. If this value is 0, only in that case integral is 0. Finally, we argue that this equation must hold for any control volume regardless of its size and shape. This is possible only if the integrated terms within the square bracket is identically 0. Hence, we have a general differential equation of conservation mass, better known as continuity equation. That is, this is equal to 0. Means this term which is within integral must be equal to 0. So this is your continuity equation. Now we know this is a vector V, but we can divide this vector into U, V and W. So derivation using an differential control volume. So we derive the continuity equation in a different way by starting with a control volume on which we apply conservation of mass. Consider an infinitely box shaped control volume aligned with axes in Cartesian coordinates. The dimensions of the box are dx, dy and dz, and center of box is shown at some arbitrary point P from the origin. The box can be located anywhere in the flow field. At the center of the box we define the density and the velocity components u, v and w. So this is your u, v and w as shown. At location away from the center of box, we use Taylor series expansions about the center of the box point P. So if point is at this point, say, we have to use the Taylor series expansions. So that is density into u at the center of the right face. This at this point is equal to, at this point, which is dx by 2 from this place, is equal to density into u plus change in density into u with respect to del x into dx by 2, because this point is dx by 2 from this point, say, plus 1 by factorial 2 into del square del u by del x square into dx by 2 the whole square. Now, because assume dx by l is equal to n minus 3, this term assume where l is some characteristic length scale of the flow domain, and when you go dx by l square, it is minus 10 to the power 6, means if you square of this term, it is almost 1000 less than the previous one. So you can neglect this term as compared to this current term, because this will be very small. So we will consider only first two terms. So this is at the center of right face. We got this equation. Same you can drive for the left face center. Same at the top, bottom, front and back. So we will get total 6 equations here. For center face, center of right face, this equation. Center of left face, this equation. Center of front face, this equation. Center of rear face. So we will get total 6 equations. The mass rate through a surface is equal to density into Vn into A. That is velocity, which is normal component of velocity Vn, and surface which is perpendicular to this vector, and density. As control volume shrinks to a point, the value of volume integral on the left hand side of equation 9.2 becomes, now take this equation. So this is control volume del p by del t dv. You can write this as, instead of dp, you can replace with dx dy z, because this is control volume. So this is the rate of change of mass of control volume, which you can write in this form. Since the volume of the box is dx dy z, we now apply the approximations of figure 9.5 to the right hand side of equation 9.2. Now this mass in and mass out you can find from this here element. This is your element here. So what is mass in? That is from this direction, from the left side, from bottom and from back side. And what is mass out? That is from the right hand side and your from front side and top side. So we can apply the mass rate into the control volume here, where dy and dz is the area perpendicular to the direction of the flow of the fluid. So in this case dy dz, because this is dy and this is your dz. So this is the area perpendicular to the direction of the flow. So we had this mass retain, which is left face, bottom face and rear face, and mass out we had this here, right face, top face and front face. Now you can put this equation of mass in and mass out into the equation 9-2. Here you will get this equation after combining and simplifying. Divide this equation by dx dy dz, you will get this equation. This is called quantity equation, coordinate system. So you can see here the material derivative pressure, which is dp by dt is equal to dp by dt can be written as partial derivative dp by dt plus v dot del into p. We can express in this form. So we can expand this equation by product rule. If you expand this, you can write this in the form of this and this. And now this term is called material derivative of density, which you can write as this d rho by dt plus this equation. And if you divide these two by density, you will get this equation. This is alternative form of continuity equation. Continuity equation is cylindrical coordinates. In cylindrical we use r, theta and z. So r is equal to under root x square plus y square. You can, this is r, this is your x coordinate, this is y coordinate, this is your theta. So r is equal to your x square plus y square from triangle law. And also this is your ur, this is to u theta. So here you can write x in terms of r, x is equal to r cos theta, y equal to r sin theta, or theta is equal to tan inverse y upon x. Now if you replace this x and y into the above equation, you can obtain this quantity equation in terms of cylindrical coordinates. So this is your quantity equation in terms of cylindrical coordinates. Now with for steady flow, this term will become 0 with respect to time will become 0, and you are left with only this term. So this is your steady continuity equation by putting this term 0 into the above equation. And steady flow for this equation, if del rho by del t is 0, then this will become is equal to 0. That is for quantity equation coordinates for steady flow, which is this equation, and this is cylindrical. Now in case flow is incompressible, we won't consider this density factor, then this equation will become, so then density is not a function of space or time, so this is 0. Also del c can be taken outside of the divergence operator, you can take out, and this become equal to 0. This is incompressible continuity equation. The stream function coordinates. Consider the simple case of incompressible two-dimensional flow in the xy plane. The continuity equation in Cartesian reduces to del u by del x plus del y is equal to 0. Now instead of u and v, we can replace this with this one single independent, or you can say dependent variable psi instead of two dependent variables u and v. So we define the stream function psi. Now psi is equal to u is equal to del u by del psi, and v is equal to minus del u by del psi by del x. Now if you put the value of this u here and this put the value of v here in this equation, this will become equal to 0, which is identically satisfied, and any smooth function of psi xy, psi is a function of xy, because the order of differentiation y, then x versus x and y is irrelevant. You may ask why we choose to put the negative sign on v rather than on u. We could have defined the stream function with the sign reverse and continue would still have the identically satisfied. The answer is that although the sign is arbitrary, but in most of books it is preferable to take this negative v and take this positive. Now take this equation on this side and rearrange. You will get this equation del y by dy by dx is equal to v upon u. What have we gained by transformation? First, as already mentioned, a single variable psi replaces two variables u and v. Once psi is known, we can generate u and v, and we are granted that the solution satisfies continuity. Second, it turns out that the stream function has useful physical meaning. Curves of constant psi are streamlines of the flow. So you can see this is your streamline, and on streamline your psi is equal to psi 1, and it is constant throughout the streamline. Means where psi is constant, these lines are called streamlines. Now along streamline, this is your dy by dx is equal to v upon u. You can write in this form. Now put the value of v and u from the definition of this function. So this is u, this is v. Along a streamline, we get this equation. Now take this streamline. Now this point is say pxy and this is point say px plus del x plus y plus del y. This is velocity v and which is this is vertical direction is v and this is u. So but for any smooth function psi of two variables x and y, we know by the chain rule of mathematics that the total change of psi from point pxy to another point px plus del x into y plus dy, some infinitesimal distance away, is this is your total change. D psi is equal to del psi by del x dx plus del psi by del y into dy. We can write it this form. Now we know this is 0, so it means d psi is 0 along a streamline. Thus we have proven that statement that psi is constant along streamline is correct, which we had assumed here, that along streamline your psi is constant. There is another physical significance factor about the stream function. The difference in the value of a stream function from one streamline to another is equal to the volume flow rate per unit width between the two streamlines. This is streamline 2, this is streamline 1, and you can say we will consider this is cross sectional area A, this is cross sectional area B. So the statement is illustrated in this figure. Consider two streamlines psi 1 and psi 2. Imagine two-dimensional flow in xy plane of unit width into the page 1 meter in z direction. So into the width, you can see into the page it is 1 meter. By definition, no flow can cross streamlines. Thus the fluid that happens to occupy the space between these two streamlines remains confined between the same two streamlines. It follows that the mass flow rate through any cross-section slice between the streamlines is the same at any instant in time. The cross-section slice can be of any shape provided that it starts at streamline 1 and ends at streamline 2. For example, slice A is smooth arc and slice B is wavy. Now we will take this here, we will consider this control volume. So we prove the given statement mathematically by considering a control volume bounded by two streamlines and cross-sectional slice A and cross-section slice B, and infinitesimal length ds, this is small, along the slice B is illustrated in figure. You can take this ds. Now this is dx, this is dy, and at this slice the velocity is v, which is a function of v and u. So n is the normal unit vector. Now unit vector in this case is this, which is dy by ds into I direction and dx by ds into j direction. Here is the negative sign because so x is in the, you can see here is the negative sign because y is in downward direction. We had to select the xy coordinate as this, x is positive, y is positive, so it is opposite, so it is negative. Now what is volume flow rate for this small element? That is dv is equal to velocity vector into this normal vector into dA, where dA is our ds, we had selected it, where ds is equal to, or you can say dA is equal to ds into 1 unit. We have already selected 1 unit into the depth of page perpendicular to your screen. We know velocity is equal to ui plus vj, and put the value of unit vector here and ds here. So this is dot product of two vectors. So expand this, you will get this equation. Now you can replace instead of u with d psi by dy stream function, and you can replace with v with also stream function. So we know total change of psi, that is also this, means you can replace this term in equation with this term. You can replace this equation with the terms of d psi. It means your volume flow rate is a function of psi. Now integrate this. We find the total volume flow rate through the cross section B slice by integrating equation this. When you integrate this from streamline 1 to streamline 2, you will get psi 1 to psi 2, and when you integrate this equation d psi, you will get psi 2 minus psi 1. It means your volume flow rate at B at this point is equal to difference of two streamline functions psi 2 and psi 1. The stream function is cylindrical coordinates. For two-dimensional flow, we can also define the stream function in cylindrical coordinates, which is more convenient for many problems. Note that at two-dimensional we mean that there are only two relevant independent spectral coordinates with no dependence on third component. Therefore, the first is planar flow, just like in the previous equation. You can see here, this is your axis symmetric body, so this is your rotational symmetry. So this is r radial direction. It can be defined in terms of x, and can be defined in terms of y, or you can say in terms of theta also. So this is your quantity equation in terms of r and theta, del r ur by del r plus del u theta by del theta. This is the same quantity equation in r theta plane. So this is your r theta plane here. Now for incompressible planar, stream function is cylindrical coordinate is equal to this. So ur is equal to 1 by r del psi by del theta, and u theta is equal to minus del psi by del r. Put the value of this in this equation, and they will satisfy this quantity equation. You will get 0 on the both side. We now note again that the signs are reversed in some textbooks. You can substitute any sign. So since order of differentiation is the relevant of the smooth function. The second type of dimensional form flow in a cylindrical coordinate is axis symmetric flow, in which z, r and z are the relevant spatial variables. So in this case, this is u direction, which is along the axis. This is your ur direction. So ur and ud are non-zero velocity components, and there is no dependence on theta. Examples of axis symmetric flow include flow around spheres, bullets, and the fronts of many objects like torpedoes and missiles, which would be axis symmetric everywhere if not for their fins. For incompressible axis symmetric flow, the quantity equation is, for this is for axis symmetric, the equation this equation reduced to this form: 1 by r del r ur by del r plus del uz by del z is equal to 0. Now in this equation again we have to define the stream function. In this, ur is equal to minus 1 by r del psi by del z, and uz is equal to 1 by r del psi by del r. So we have to define ur and uz in a way that when you put this value in this equation and this value in this equation, the overall it will satisfy it, and you will get 0 on this side of the equation. Conservation of linear momentum, Cauchy's equation. Application of Ronald's theorem, transport theorem. We had a general expression for conservation of linear momentum applied to control volume. This is our control volume here. So the momentum, linear momentum, that is the summation of all the force, is equal to, this is control volume density g into dv, plus this is control surface integral sigma ej dot nda, where sigma is your stress tensor. So now so sigma ej is a stress tensor, is you can see this on this control volume. Sigma ej on the positive face of an inflationary rectangular control volume is shown. So this is sigma xx, this is on the x side, this is sigma xz, this is on x and z side, and this is xy, which is on xy side. Same on this plane, this is sigma yy, which is only on the y plane, and sigma yz, which is on this plane, and sigma yx, which is toward this x direction, and y, because it is at this surface. Same for the, you can express for this surface. So this is your tensor quantities. Now force can be expressed as body force and surface force. This is your body force. Surface force, this can be expressed in terms of this, where v is the last two terms is taken as the average velocity at the inlet and outlet, and beta is momentum flux correction factor. In other words, the total force acting on control volume is equal to the net rate at which the momentum changes within the control volume plus the rate at which momentum flows out of control volume minus the rate at which momentum flows into the control volume. We can use divergence theorem. Now what is divergence theorem here? The extended divergence theorem, which is Gauss theorem. So we will take is here Gi and we will replace this with the quantity, that is density into velocity into V, a second order tensor. So this is a second order tensor. The last term in equation 932 becomes this density V dot N dA is equal to del dot density VV into dV. So we can take this term and by using apply Gauss theorem we can convert into this control volume, where VV is a vector product called outer product of velocity vector with itself. The outer product of two vectors is not the same as the inner or dot product, nor it is same as the cross product of two vectors. Similarly, we can replace Gi in this equation by stress tensor sigma ij, the second term on the left hand side. You can replace this term with sigma ij, then it will become integral control volume del dot sigma ij dV. This is, you can also replace, this is the second term in this equation, which is sigma ij control surface. You can convert it to control volume by using Gauss theorem. Now take these two equations, replace this with the control volume with the Gauss theorem, and replace this quantity with the help of Gauss theorem with the ball control volume. You will get equation. So you will get this equation by from 932 by using this equation and this equation. In 930 you will get this equation. So which must hold for any control volume regardless of its shape or size. This is possible only if the integrator enclosed by square bracket is identically 0. Definitely if integration of this to be 0, it means this must be equal to 0. So this must be equal to 0. When you get this to 0, you will get this equation, and this is called Cauchy's equation, conservation of linear momentum. This is a differential equation for conservation of linear momentum. The Navier-Stokes equation introduction. Cauchy's equation is not very useful to us because the stress tensor contains 9 components, 6 of which are independent. Thus, in addition to density and 3 velocity components, there are 6 additional unknowns for a total of 10 unknowns. So it is very complex. We can replace with the less components. The first thing we do is to separate pressure stress and the viscous stress. When a fluid is at rest, the only stress acting at any surface of any fluid element is the local hydrostatic pressure P. So this is local hydrostatic pressure P, which is same from all direction and which always acts inward and normal to the surface. So fluid at rest, we had this equation. This is your tensor vector sigma ij. We can write in this form. But we know there is only one stress, that is in the form of pressure in case of a fluid element, that is P. So that is XX in this direction, YY in this direction, and ZZ in this direction. So rest other are 0. So you can replace this with this. The hydrostatic pressure in equation is same as thermodynamic pressure, which we are familiar from our study of thermodynamics. P is related to the temperature and density through the some type of equation of state. As a side note, this further complicates the compressible fluid flow analysis because we introduce yet another unknown, namely temperature T. This is now unknown requires another equation, the differential form of energy equation, which is not discussed in this text. So when your fluid is moving, so viscous stress may also exist. So in that case, your this tensor stress sigma ij will become, this is your pressure, fluid pressure, and this is your viscous stress tensor. Mathematically, we have not helped the situation because we had replaced the 6 unknown components of sigma ij with 6 unknown components of viscous stress tensor ij, and we have added another unknown pressure P. Fortunately, however, there are consecutive equations that express sigma ij, or you can say tau ij, in the terms of velocity field and measurable fluid properties such as viscosity. The actual form of consecutive relation depends on the type of fluid as discussed. If fluid is incompressible, we have no equation of state. So, and we can no longer define P as a thermodynamic pressure. Instead, we define P as a mechanical pressure. So this is your mechanical pressure, which is minus 1 by 3 sigma xx, sigma y and sigma zz. We see from this equation that the mechanical pressure is mean normal stress acting inwardly on the fluid element from all the three faces. So we will take sigma xx component, sigma yy component, and we will take sigma zz component, which is here. It is therefore also called mean pressure by some authors. Thus we are dealing with incompressible fluid flows. Pressure variable P is always interpreted as a mechanical pressure Pm. Derivation of Navier-Stokes equation for incompressible isothermal flow. We limit our discussion to Newtonian fluid, whereby definition of stress tensor is linear proportional to the strain rate tensor. So your stress is proportional to strain rate tensor. These two are tensor quantities. So here stress is proportional to strain. The general result for compressive flow is rather involved and is not included here. Instead we assume incompressible flow, and we also assume isothermal flow, that there is no change in temperature. A further consequence of later assumption is that the fluid properties such as dynamic viscosity and kinetic viscosity are constant. So we know viscous stress tensor for an incompressible Newton fluid with a constant property is equal to, so this is your viscous stress tensor, which is equal to 2 times viscosity and your strain rate. This is strain rate tensor in Cartesian coordinate, which is this Eij, which is this here, total 9 terms, and individual term is expressed here. Now you can place the value here in this equation for the strain, and you will get the viscous stress tensor in this case, in this form. Now we know that this is your stress tensor, which is a sum of pressure and this vector. So this is our stress tensor, which is equal to this. Now put this equation here into the three coordinate components of Cauchy's equation, into this equation. First in this equation you will get x component, then y and z component, so on. Now putting into the first equation, you will get this equation here. While taking this sigma xx, you have to consider the component, which is this component plus this component, which is this and this component, while taking sigma xx, and so on. While taking sigma yy, you have to take this component and this component, and during z you have to take this component, this component. We note that as long as the velocity components are smooth functions of x, y, z, the order of differential is irrelevant. For example, the first part of the last term, take this term, this part of, you can rewrite in this form, that is mu del by del z, del w by del x. You can replace, you can interchange, you can take del x out, del z inside. You can interchange this first part with this term, and same you can do on this term here. For the first part of this term, you can interchange del by del x, and for this equation you can write as this also, this plus for the half part you can write as these two are same. So it will come, it will, if you add these two, it will become same as 2 into del g square v by del x square. Means this equation can be written in this form. Now take del by del x outside, take common, you will get this form. The term in the bracket is 0 because of continuity equation for incompressible flow. We also recognize that the last three terms as the Laplacian of velocity component u. You can take these last terms, you can write in this form also, del square, where del square is equal to this. So this is a Laplacian operator. So you can write instead of this as del square into u Laplacian. So our equation becomes this. So this is your first equation. Again you can write the same for y and z. You will get this second equation and third. And when you combine these three equations, you will get Navier-Stokes equation for incompressible flow with constant viscosity. So this is your Navier-Stokes equation.